So hello everyone, in this video we will see how we can use Design Expert software to optimize any process or experimental condition. So for optimization we will use the Design Expert software version 13. Before going to use this software, we need a basic some theory behind what software does, how the designs are made. We will look into that and then we will come to the software and we will optimize our experiment. Once you will get into the new design, you will get you will get various options over here. There is a full factorial and there is a response surface. Inside the response surface, central composite design is there, box beacon is there, and DSD is there. So for this video we will understand how particularly central composite design, how it design any experiment and what are the next step that involved in the Design Expert software. See, we all know that the optimization is very essential for our experimental condition. So there are various method of optimization like analytical method, stochastic method, and there are various other more methods to optimize. An analytical method mostly used as gradient descent, and there are more. In stochastic method, when generally most commonly used as a genetic algorithm, and there are various methods. So Design Experts software is mainly based on the analytical approach, where we use analytical approach to optimize our process condition. So Design Expert software work like you provide based on your design, they will provide certain number of runs and then you will give response to them, and they will plot their response based on input, something like this, and then they will try to find this fitting function. So once they will find the fitting function, then software will try to find the global maximum. In this we can see there is one more maximum that is called as local maximum, and for suppose our desirability is to find the maximum value of our response. In that case they will try to find the global maximum, and that will call as the optimum condition for your experiment. We will see that one in Design Expert software interface, how they are disintegrated into different sections to get the optimum condition. So I will disintegrate Design Expert into three sections. One, the Design Expert, what it does, that it create a design for you, like what sort of design you choose. Based on that they will give number of runs for your experiment, like whether is your full factorial, CCD, BBD. So based on that it will design for you based on your input, and then they will ask for response. You have to fill it out. Once the design you have provided to the software, then what they will did, they will analyze it, where you will get ANOVA data and fitting function for your next step, and based on that fitting function it will optimize for your experiment and you will get that desired condition. Coming back to the basic, like if we see the full factorial, and if we have two variables a and b, in full factorial having two levels, low level and high level, -1 and 1 plus 1 represent low and high level. So this will be the combination, and the total number of runs will be the 4. By combining -1 to these two and +1 to these two, you will get these 4 runs. And if we see that what's the formula for total number of experiment, it will be as a level to the power factor. So if we have level 2 and factor is also 2a and b, so 2 to the power 2 we will get 4 as our output. If we see the design how it will look like, so this is the how these two factors will look like. So these all are the coordinates and the design will be look like this. If we increase one more factor, here we have 3 factor a, b, c, and each factor having 2 levels. So total number of experiment, what do you expect? 2 to the power 3, because level is 2 and factor is 3. So total number of experiment will be 8, right? So the formula will be the same, level to the power factor. Somewhere factor will be also written as a k, so it's up to you. So if we see the design of 3 level factor, it will be look like something like this. Okay, so these 3 low level for each factor represent this point, and these 3 high level of each factors is represented by these points, and there are all 6 other points. Okay, the next is like why we need central composite design if we have already full factorial. The problem with the lies with the full factorial that if they have only 2 levels, in that 2 level we can only get the straight line. If we have to see the curve effect, we need additional point, and then we can see the second order, third order effect on our experimental condition. For that we need additional point, and that can be resolved using the central composite or using the central composite design. So how the central composite art design is made? So central composite design use the full factorial as a base. So it has already full factorial. Additionally, what they do, it also add few central points, approximately 4 to 6. You can add more, and then additionally it also add axial point. So we will go each individual input. So let's talk about CCD having the full factorial as a base. So this is the design of a 2 factor where it is a full factorial design. If we add the center points, suppose here we have added 4 center point, it should be overlap, but for your visualization I have kept it like this. So it has full factorial. Now it has also the 4 center point. Now if we add the axial point, so this is called as axial point. There each factor will have 2 points. So it help us to get good second order surface for optimization application, right? So if we see that, so if we have only talk about the number of factors, if we have only talk about the 2 factors, if there will be more factors, then what will be the total number of runs? So it composed of 3 things. So full factorial, we know that level to the power factor, so level will be 2 to the power factor, and the center point, it's up to you how many you choose. So for now we choose 4, so we will write 4, and axial point 2 into the factors. So here we have 2 factors, so it will be 4. So total number of run will be the 12. If we see if we have a 3 factor, then what will be the case in that one? See, this is the full factorial design for 3 factor, and then we again add the 4 center point, and again we will add the axial point. So here we have 3 factors, so there will be 3 axes, and each axis having 2 end points. So how many runs will be there for this design? So 2 to the power 3. So we have 3 factors, will be 8. We choose the number of center point 4, and 2 into 3 will be the 6. So total 18 experiment will be there for this 3 factor experiment. Okay, the next is if you see these I'm considering 2 factor and 3 factor at a time to better understanding. Question is like, we know the factor condition like low level, high level for each factors. We know the center point for each factors. The question is, what will be these axial value, and what we call this axial value? So what will be the next question? What will the value of the axial point? So fade out the other things, we will focus on this axial value. So this axial value is called as alpha, and alpha can be anything. Based on this alpha, CCD is again divided into different sections. Now, what are the types of CCD based on alpha, and the value of alpha will be decided on that only. Suppose this is the full factorial for 2 factors, and we have 4 center point, and this is designed like this. If we eliminate for now the center point, and we will focus on these only. If we draw a circle, so that circle will goes through each points. In that case, this is called as circumscribed CCD. Right now we will only see that type of CCD based on alpha, then later on we will see what will be the value of this alpha. Okay, so if we have full factorial like this, we have not considered center point, and then the value of this axial will lies on this face of this square. In that case, it will be called as face centered CCD. Next is, if we draw a circle again to the this point, and then in this case it will called as a inscribed CCD. Did you notice anything difference? In the first case we have similar kind of things, and here also it is a similar design. Then why we call it inscribed? You see notice the value of this extreme value. Assign this extreme value as low and high, and this factor will be somewhere lesser than the extreme value. So in that case we called is a inscribed CCD. So we have shrunken the full factorial value. Now if we plot these three type in one, so here we have lower value and higher value, lower level and higher level, circumscribed CCD. So this factorial line will pass through the factorial, and this alpha value go beyond these two level. At the same time, this phased CCD will have the same axial point as the factorial, whereas inscribed one, the extreme value will lies on this line. So this one is CCD, and this one is phase central CCD, and this is inscribed CCD. So first one is rotatable. Let me show you again. So if you rotate this one, so it all point will lies on this circle itself. It will not goes that. And again inscribed is also rotatable. So these all terms will see on the software as well, where is rotatable, where is not. So do not worry about that one. So what CCC? Explore the largest process space, obviously. So this process space over here is lies between -1 and +1, whereas the space will goes beyond +1 and goes beyond the -1 value. The next point is CCI, inscribed one, explore the smallest process space. Both CCI and CCC is rotatable design, as we have seen this, whereas CCF is not rotatable, obviously. So for three factor, CCC and circumscribed design point describe the sphere around the factorial cubes. This means that if we have one more factor, then it will become cube, so there will be sphere around that cube. If we see that rotatable nature, so each factor will have at least 5 level. Well, and if we see that face centered, each factors will have 3 level. What I means to that, if we see this particular factor A, so particular factor A, to design this, what will be the value for A? One will be this minus alpha, -1, and this center value +1 and alpha. So how many value will be required for the A? 1, 2, 3, 4, 5. So for circumscribed, we require total 5 level for each factors, whereas if you see the face centered, how many level for each factor is required? For if we see the factor A, so 1, 2 and 3. So only 3 level is required for each factor for the face centered. Now coming back to, we have understood based on alpha we can categorize the CCD into different category. Then what will be the value of this alpha? For rotatable design, which ensure that constant prediction variance at equal radius distance from the center, alpha is calculated. So alpha will be calculated number of factorial runs to the power 1/4. So we know that the factorial runs is based on full factorial, so we can write 2 to the power f to the power 1/4. If we have number of factor 2, so total factorial design will be 4. This one is the factorial design, not a composite design. So the alpha value will lies this value. Again the factor will increase, so full factorial value will increase, and then corresponding alpha value will also increase. If we assume for circular or spherical, in that case the alpha value we can calculate as like, if the distance between these two factor is -1 +1, so it will be the 2 and this will be the 2. So what will be the gap between this? If we use the triangle formula, 2√2. So the distance from the center to this value will be equal to the distance from center to this value. So it will be the half of the diameter. So that will be the alpha value equal to the -√2. That will be 1.4142. If we assume spherical, so in that case this is 2, this is 2, and this is 2. So this will be the 2√2 and this is 2. So obviously the diagonal will be 2√3, and the radius of this will be divided by 2, so root 3. Distance from the center point to the factorial point will be same as the distance to this axial point, so alpha value will be the root 3, and that is 1.73203. You will understand in much clear way if I will show you these things on the software which we will use in the coming videos. Let me show you the first the software, then you will get clear understanding why we are discussing this. If we we have 3 factor, and in the 3 factor we will see these things in later, but for alpha value I'm showing this interface. If we go to the option, like for particularly alpha there is a different option. We have seen that if there is a rotatable, then each factor you will get the different value. As we seen, if there will be a spherical, as just now we have seen, the value for 3 factor is 1.7320. And then there is one more thing, there is a face center. Obviously if it lies on the face, the value will be 1. That will be the whatever the value of the factors. There is one more thing, if there will be practical, so what will be the value of the alpha? Okay, so the next thing is if it will be the practical, for by default CCD option for alpha is set, so the design is rotatable. This give higher extreme value. Okay, usually by default whenever you will open the design expert, the alpha value will be set on the what? A rotatable design, so that is where you will get extreme range of alpha value. If you want a practical value for alpha that is less extreme, where you don't want alpha value to go beyond certain level, so you need a less extreme, in that case the practical alpha value you can use for your optimizing your design expert. And here the alpha value is just like earlier one, but only thing is here the number of factor is here, not the full factorial. So we can see this, the number of factor is f, and then the formula for alpha value will be obviously for each factors will be to the power 1/4, and you will get the alpha value for the practical. So here we are again. So this is the Design Expert software version 13. Once you will go to the design, a new design, and inside the response surface you will find the central composite design. Here you know that how many factors is there in your experiment. For now, if we can assume that we have 3 factors, again this is a numerical factor, that means your factors will be in, again the alpha value is it's a failure, you cannot change it. You have to decide from here what will be the alpha value. As already discussed, there is one more thing, that there is a replication. For your designing, it is always if you design your experiment, you should consider the replication. What I mean to see that if we have each replication, and for now if we have 6 center point, if we increase the factorial replication, that means this from this design one more only factorial design will be considered over here, so that will increase the number of runs. If we also increase one more factorial design, so again the number of runs will be increased for our experiment. Obviously you have to do in duplicate and triplicate your experiment for your get robust optimum condition. And if we increase the replication in your axial point, that is again will increase the number of runs for your experiment, although it will give the pretty good optimum condition for your experiment. Let it be at 1 for now. Once you will decide all the condition, and for now we will choose as a face centered, so we will get 20 runs, and then we will click the next. So here they will ask how many response is there. For now if we have only 1 response, okay, and then once we will finish it, so we will get the design for our experiment. In the next video we will see how to fill this design, and then what are the next step to analyze this design, and then how we will optimize those value, and we will get the optimum condition with the most desirable value. Thank you so much.